Section 4.1 introduces vector spaces and along with that subspaces. So this is really just a generalization of our idea of vectors in real spaces like Rn. So it turns out that the operations we've been used to, adding two vectors together, scalar products of vectors, that more or less makes up the space in the algebra on the space Rn, our real space of n dimensions, generalizes quite nicely to even larger or even broader types of sets that aren't simply just real numbers. The most natural extension would be to go to the complex space Cn, where the space of complex numbers of n dimensions, where instead of a real number in each entry, we have a complex number. But that's just a small extension into a new space. Beyond that, we can talk about vector spaces of functions as well. And this becomes a really useful topic in something like differential equations, where you might be searching through a space of functions, or you might desire some properties in a space of functions in order to determine the solution to a system of differential equations. It has far-reaching applications throughout mathematics, though not just differential equations. But through all of this, what we can keep in mind is that even though we're going to build an abstraction of the space Rn, we can still consider Rn, the real space we've been dealing with, of n-dimensional vectors with entries which are real numbers. We can still think of that as the canonical example of a vector space, right? Our sort of central pillar, our main intuition for what a vector space is or what it's like. Now, when that's useful, that's a great tool. It's a great intuition to have or analogy to work with. But at times you'll have to suspend that, because not all spaces are finite dimensional, right? Not all spaces are n-dimensional. We might see that there are infinite dimensional spaces, which we might touch on a little bit here, but we won't really generally deal with results in an infinite dimensional vector space. We'll just deal with the finite dimensions, and that's suitable enough, and that gets us to a lot of places. So let's jump right in. Now, what is a vector space? So a vector space, we need to make formal, right? We already have some idea of what a space of vectors is like. We've dealt with spans of vectors and looked at R3 and R2 and these sorts of things. But we have not formalized this notion of a vector space. So it turns out, in order to do so, we need these 10 properties. So if we're going to let V be some non-empty set, and we're going to define an addition of operation and an operation of addition and an operation of scalar multiplication, the scalars taking values in some set F. We use the word F here because this set is typically required to be a field. We don't really need to know what that means for our purposes in vector spaces, but just know that that's the formal mathematical body from which we take our scalars. This must be a field. Rest assured that the real numbers are a field of numbers. So we often refer to the real numbers as the field of real numbers. Anyway, so we have scalar multiples or scalars from some set F with vector addition and scalar multiplication. So a vector space satisfies all of these. Closure under addition. The first two are some of the most important. For any two vectors u and v in our space V, the sum u plus v is also a vector in our space V. So that's what closure means. If we do the operation, we don't leave the set V. We remain in our set V with our sum operation. Similarly, for closure under scalar multiplication, if we take a vector V that's in our space, we multiply it by a scalar k in the field, we arrive at, we end up with a vector that's still in our vector space V. So that's closure under scalar multiplication. We don't multiply some vector by a scalar and end up outside of our space. So furthermore, commutativity of vector addition, associativity of vector addition, these start to look like very common things. And in real spaces, there are things that we can sort of take for granted, because we're a space of real vectors or vectors with real number entries. All these properties are inherited from the fact that the entries are real numbers. In more general spaces, these might be less trivial things to prove. And we'll do a little bit of proving, or at least confirming that spaces of numbers or otherwise are actually vector spaces and satisfy these properties. Now, the existence of a zero vector. Of course, for a real space, that makes perfect sense, but in an abstract space, something like the set of polynomials as a vector space, well, then we'd have to consider what the zero vector is in that space. We might see that later. Existence of additive inverses, right? So there, for each u and v, there's a negative u and v such that when we add them up, we're equal to that zero vector of the space. The unit property, the scalar, there's a scalar unit in each vector field. That's part of how it's a field. It has a number like 1, for which multiplying that scalar by a vector results in that vector. Associativity of scalar multiplication, as is here. Distributed property of scalar multiplication over vector addition. So scalar times the sum of vectors is distributed. And then distributed property of scalar multiplication over scalar addition. So we can do something as follows here. All 10 of these conditions have to be met for a space to be a vector space, which means to prove that a space is a vector space, we have to actually confirm all 10 of these. And they're not as straightforward as you think. In the real numbers, these are problems, we usually call these properties, not conditions for the definition of a vector space. So things are really kind of starting to turn backwards on us. It turns out the real numbers as a field has so many useful properties that we actually formalize and abstract what this idea of the real numbers is with its operations, and it has similar characteristics as this vector space here as well on its own. So these properties were so useful for our real space of vectors that we extend that into a general vector space as well, and that's the big idea. It's easy to see that these hold for real vector spaces. It's not as trivial often for other spaces, but nonetheless, we'll still visit some of the properties of vector spaces for real spaces and confirm that they're actually true, and that the space Rn that we've been dealing with under vector addition and scalar multiplication is in fact a vector space. So informally confirm each of these is true, or that yeah, so whatever we have here, that each of these sets is a vector space. So the real numbers under the usual operations of addition and multiplication is a real vector space. So the real numbers being really what we're saying now is, in this case, V is the set of real numbers, and the field F is also the set of real numbers. We can think of this as R1, one-dimensional real space. So yeah, like I said before in the previous page, real numbers satisfy all of these properties. We could go through and confirm that this is the case. It would be fairly trivial. There's a 0 in real numbers. There's a 1 in the field of real numbers, for which 1 times anything in the real numbers is going to be that thing in the real numbers, and so on. So that's trivial, right? Nonetheless, it's a good exercise to go through and confirm all these things hold if you have any doubts. Going a little further into it, the set of complex numbers as a vector space. So we take the set of complex numbers under the operation of addition of complex numbers and multiplication by a complex number form a vector space. We could also multiply by a real number, and this is actually what I have written here when this example is actually telling me we're going to multiply not with real numbers, but with complex numbers. So we're going to take R and S. These are our scalars. They're actually going to be complex numbers as well. And it turns out the complex numbers also form a field, and so they're an appropriate choice, right? So this is our field, and this one is our vector space V. Now these are a little bit trivial so far, but we'll push past that in a little bit. To really show that this is true, we'd have to show that all the properties hold. Well, we know that if we add 2 complex numbers, Z1 and Z2 together, then we'll get another complex number. We'll see these things demonstrated. I'll do a full demonstration in the next page for the complex numbers being a field or a vector space under the field of, I believe we use real numbers on the next page and not complex numbers, just to make it a little bit more easy. So part C, the set Rn with the operations of vector addition and scalar multiplication by a real number is a real vector space. This is the space we've been dealing with, talking about the same vector addition we've been dealing with, and we'd go through and check off that all of these things actually are true. Well, think about this one. How do we know that if we take 2 vectors in Rn, n-dimensional real space, and add them together, that we get another vector in Rn? Well, all of the entries in V1 and V2 are real. So when we add each of these entries together, we'll have a real number in the new entry or the result entry, and that's going to give us a vector of real numbers that's n-dimensional, so we'll know it's in this space. Some of these things are kind of trivial to write down, but nonetheless, we do have to show technically that the spaces we call vector spaces are in fact vector spaces. So here's a nearly thorough example, and I'll just leave this more, I'll go through some of it, but I'll leave this more as something to read in the notes on your own, or to zoom in and have a look at. We prove here that the set C with operations of addition, and I actually did use complex scalar multiplication, so it's just like the second question on the previous page. We're asked to show that this is a vector space. So this is the laborious work of going through and showing that all of these properties hold for complex numbers. The main two, the most important two, are A and B typically. I will do some of these and leave others for exercises. You see little gaps where I've said, okay, a student can fill out in the details right here. But the primary step to one of these is to instantiate necessary variables for this demonstration, right? So I've instantiated 3 complex numbers, Z1, Z2, and Z3, all in V, elements of V, the vector space we're talking about, which is really the set of complex numbers. And then I've instantiated 2 scalars, because we'll need those, that are also in our field F, which happens to also be the set of complex numbers. It could have been the real numbers instead, nonetheless. And now when I go to show that Z1 plus Z2 is an element of V, I have to decompose these things. Well, I know that complex numbers have this form, A1 plus B1 times I, where A1 and B1 are real numbers, and the I is what makes this the imaginary part, makes this number complex overall. And then I do the same for Z2 with A2 and B2. When I add these complex numbers, I'll have a real part, and I'll have an imaginary part, and I have a form real number plus an imaginary number. And that's exactly what a complex number is. So I know that this space is closed under addition because I get another complex number. Now, if I multiply part B, scalar multiplication, if I take C, which is A naught, B naught, or plus B naught I, if I multiply that by Z1, then being careful to recall that I squared is -1, I have a real part that looks like this. This is B naught times B1 I for each of those. And when we have I squared, we have a negative. So we have a real part here, and then an imaginary part. And again, real plus imaginary leaves me in the space of complex numbers. So I proceed like this through all of these steps. I'll leave commutativity is the next one, right? We break it apart. We write it down like this. Then we commute the real numbers, because we know that real numbers commute additively. So we commute the real numbers, and then we rewrite it as the complex numbers. This is formal proof writing in action, right? These are all the details that need to be written down in order to prove that this is in fact the case. Because if you assume something's a vector space without actually showing it, and you get it wrong, you're going to assume it has a property that it doesn't in fact have, and that could be that could cause problems in whatever it is you might be working on. Associativity follows very similar to commutativity. I left that as an exercise. There's a 0 vector in the complex numbers. Well, it's the number 0, but it's the complex number 0. And what I didn't write, well, I did eventually write this. I wrote 0 plus Zi, and I wrote 0 plus A1 plus Bi for Z1. Now I expand 0 into its complex form. That's technically the 0 complex number here, with a 0 for both real numbers. And, skipping some details of adding 0 to A1 and 0 to B1 and their respective components, and coming out with A1 plus B1 I, we end up with Z1. What I didn't show here is that this 0 vector is unique. We'll see some examples of how to show that momentarily. That's the other thing we have to show, that the 0 vector is unique in this space. In other words, there's not some other complex number, call it C maybe, for which this property works as well. And that, as silly as it seems, does have to be shown for any space we might be working with. Let's see, negative Z1 plus Z1 equals 0. This is the additive inverse line. And we see that, yeah, negative Z1, well, that's defined as this. We expand Z1. And, well, we add to that Z1, and then we add by components, we get 0 plus 0i, and that's, of course, equal to the 0 vector in complex numbers, or the number 0 in complex numbers. A unit, 1 times Z1, right? Well, we know again, all these properties are inherited from the fact that they're true for real numbers. That's the primary, that's where this comes from. Of course, we would accept that 1 times a complex number is that complex number, but to be very formal about it and show that this is necessarily the case, it's inherited from real numbers. The fact that 1 times A1 is A1 and 1 times B1 is B1, and then we can arrive at this. So we're showing in a way that possibly we've never shown as thoroughly before that complex numbers behave very much like real numbers, and that they're in fact vector spaces. So the rest of this is a constant C. This is the associativity of constants. A lot of details to write down here, but I started this problem out for folks. And that could be continued for students who are interested. The textbook might even have the example of this as well. And the same for the last two. This is the distributive properties for vector addition and for scalar addition. So there's a lot of work to do in these, and luckily we're going to see a shortcut for subspaces when we get to that. Now, what's a more interesting space? So complex numbers is not it's not a very big generalization of real spaces. We just have tuples now, two tuples, right? A complex number is a real and an imaginary part. So you can think of it as a 2 vector. That's not really, it's not much different than a real vector space. Now, let's think more about real valued polynomials with real valued coefficients. And we'll call that, so all the polynomials with degree n or less will denote that as P sub n. Well, this is also a real vector space. We could go through all 10 of the properties and show that in fact holds for polynomials. Again, the method of proof is very similar. We let P, Q, and R be polynomials in n. So I might have technically said P of x, Q of x, R of x be n degree polynomials, or in the set P of n means that they have as high of a degree as n, and not necessarily, right? It's less than or equal to n. And then we have real constants R, S, and T. Maybe we just needed RS. I wrote down a few, or an extra one just in case. But closure of addition. So we take two polynomials P and Q. P has the form P naught constant plus P1x plus P2x squared all the way up to Pn x to the n. Some of those coefficients might be 0, right? But this is the general form of one of these polynomials. Q is similar, general form up to xn. When we add these two polynomials, we add like terms. Q naught and P naught add together. P1 and Q1 add together as the coefficients of x. What we arrive at, it's a little less trivial than what we've seen before, but we have a constant term, then we have an x to the first, an x squared, so on, coefficient all the way up. All of these are real number coefficients for a polynomial that has at most degree x to the n, and it turns out that yes, the sum of these two polynomials remains in this space, and we do have closure of addition, closure of vector addition here. Now, constant, scalar constant times a polynomial p, well, we can distribute r times each of these terms because, well, that's a property of the real numbers. So we do that, and we see that we have r p naught plus r p1x all the way up to r pn x to the n. And when we look closely, these parentheses coefficients are real numbers also, times powers of x up to x to the n. That is an element of Pn, a real coefficient polynomial of degree n or less. So everything still holds. Now I skip a few. I go down to the 0 vector because that's interesting in this case. Nonetheless, these details would need to be filled in to actually prove this, but I'll leave that as an exercise. What's the 0 vector in this space? Well, interestingly enough, the 0 vector is just the 0 polynomial. It's identically 0 for any x value. And what that means is, well, that's a polynomial with x to the n, you know, as its largest term here, with zeros as all of its coefficients. So of course that's going to be 0. And when we add the 0 vector to any polynomial, well, we do it coefficient wise, and we're going to end up with, of course, what we expect, but writing it down is still necessary, our initial polynomial p. So there is a 0 vector. Now we would have to also show that that 0 vector is unique too. That's another secondary follow-up, and as well as the last 5 properties of this vector space as well. But these are the interesting ones. I believe the book does a thorough job of this, and digging through all of it in a video is not a great use of time. So let's see maybe some results on vector spaces real quick. Turns out the zero vector is unique anyway, or maybe that wasn't required. Sometimes, let me see our definition real quick. Sometimes it's required that the zero vector be unique. No, okay, good. In this case, we don't require it, and it turns out it is already automatically unique. Or maybe I'm just mistaken about that fact in general. So in a vector space, the zero vector is unique, and that's proved as a result. So my mistake for saying that these things needed to be unique. But it'll turn out that it truly is anyway. The way to show that, if V is a vector in V and it's the zero vector, well, then we already have a zero vector denoted as 0 here. But if 0 is another vector, or like it is a zero vector, in other words, it has the property that V plus another vector is equal to that other vector, right? This is the property of Z being the zero vector on the right here. But we also know that the zero vector plus V is going to be equal to V as well. Both of these things hold. But we also know that these are things to fill in, right? And I'm kind of answering the why that's asked right here. We also know that commutativity holds in vector spaces. That's one of the conditions. And now we're assuming that V is a vector space. So commutativity has to hold. So we know that 0 plus V is V plus 0. So if we start here, V is equal to 0 plus V. So that's that line. Then we can commute that because 0 plus V is equal to V plus 0 thanks to commutativity. And that's equal to 0. So we get this line here. So we can conclude by transitivity, looking at either end, that V is 0. Right? So if we have another 0 vector, well, it turns out it's equal to the 0 vector. So that's uniqueness, right? If it's any other vector with the 0 property, well, then it must be the actual 0 vector. And we've just demonstrated that. So the 0 vector is unique. Line 2, a scalar times the 0 vector is equal to the 0 vector for any scalar whatsoever. It's probably something we expect, but nonetheless needs to be proved if we're writing it down as a property here, or as a result from vector spaces. So we start with a vector u and v, 0 times u. We can make some space here and write 0 as 0 plus 0 times u, because of course that's true in the real numbers or in our field. The 0 of a field is that element in the field for which it plus something else is equal to something else. The additive identity property, additive identity element. We know we have distributivity for scalars, so we can distribute 0 times u plus 0 times u, as we've done here. Now this equation is equivalent to, we'll take this side and this side, and we'll subtract 0u from both sides. There's a negative 0u vector in the space, right? Because there are additive inverses for each vector. So we do that by subtracting each of these from either side of this equation. And what we end up with is that 0u, well, we have 0 and 0 thanks to these sums as vector. And we arrive at, well, there's a property here that 0 plus this vector 0u, right? Being very pedantic about all of this, right? And preserving these terms until we've used the actual properties of the vector space to arrive at the next step. This is exactly the additive identity, or the additive identity element of the vector space 0 property. Right, so here's our 0 vector sum is equal to that vector. So it turns out in this case that 0u is equal to the 0 vector. And that's exactly what we were hoping to arrive at. Just this is I did number 2. I highlighted number 3 earlier, but all along I was talking about number 2. A similar result holds for number 3. This is also done in the textbook, I believe. We can write following ku plus k0, and that's equal to k times u plus 0 by distributivity, and we arrive at this is equal to ku, because u plus 0 is the 0 vector is just u. That tells me that ku is equal to KU plus K0, and that we could deduce that tells us that K0 is equal to 0. The rest of these are exercises, or you can look them up in the book, but these are nice properties to have. We have a look here. The additive inverse of each element in V is unique. Do a similar proof as part 1 up here, most likely. You assume they're multiple and then show that they happen to be equal to each other. For all U and V, we can build the additive inverse vector for U by multiplying by the -1 of the field that we're working with. And then if K is a scalar and U is a vector in V such that KU equals 0, then either one of these two is 0. Right? Either K is 0 or U is 0. And that's the only way to get that 0 vector out of that product. So continuing, subspaces. Now we're going to take essentially a subset of V, S, a non-empty one, that is. We have a non-empty subset of V, which is S. S is itself a vector. If F is itself a vector space under the same operations of addition and scalar multiplication as V, then we say that S is a subspace of V. So let's look at a non-trivial subspace here. Let S be the set of all real symmetric n by n matrices, and then verify that S is a subspace of the set of all n by n matrices. So the space M sub n is n by n real matrices. Now our space S is real symmetric matrices. So those are matrices that are symmetric. In other words, those are matrices for which A transpose is equal to A. So in other words, when we transpose the matrix, it's equal to itself still. Okay, not all matrices satisfy that. But it turns out that this is a space, this is a subspace of the set of all n by n matrices with real entries. So I start to prove most of these, but I stop after the first two, and we'll see why in just a second. We could go through and hammer out all of the properties, these 10 properties, for this being a subspace, but we'll see that that's not necessary. So we let A, B, and C be in this space S, so they're symmetric matrices. All three of A, B, and C satisfy this property. And then we give ourselves some constants or scalar multiples. A plus B transpose. Remember how to take the transpose of a sum. It's the sum of the transposes. So we do A transpose plus B transpose. And we end up with, well, A transpose and B transpose are each equal to A and B respectively. So we know that A plus B transpose is equal to A plus B. So that tells us that the sum of A and B is symmetric. If we call this matrix maybe D equals A plus B, then D transpose would be equal to D. So we know that the sum of two symmetric matrices is a symmetric matrix, and we have closure under addition of symmetric matrices. So if we add two symmetric matrices together, we get another symmetric matrix. And that's a kind of an interesting fact on its own, but it's a really great example of a vector subspace, as we're seeing. Now, R times A, scalar R times the matrix A, take the transpose of this scalar multiple of the matrix A. We can immediately write this down. Why can we do that? Well, it's coming from a former result, I believe back in chapter 2, maybe section 2.1, properties of matrices or matrix operations. We saw that this property held, the one along this equal sign here. But anyway, once we get there, we have A transpose, and we know that A transpose equals A. So we have R times A on our right-hand side. And what that tells us is that the matrix R times A, its transpose is equal to the matrix R times A. So that tells me that the matrix R times A is, oh, I wrote the wrong thing here. I should have written, this is S. This is our set of symmetric matrices. S. So we are in S. I should have done the same up here as well. That's misleading. We need to be in the subspace, not just the host space of V. The zero matrix is worth identifying right here. So putting 0 in brackets when the size of the matrices we're dealing with is known by context. In this case, we're dealing with n by n's. This is the 0 in brackets is n by n entries of zeros, right? And clearly transposing n by n entries of zeros is going to be equal to n by n entries of zeros, and we end up with there being a zero vector in the space of symmetric matrices. And again, though this is true, we're not trying to prove that, we're trying to prove that S has a zero vector. It is true that the zero vector is also in the space of n by n matrices. It's an n by n matrix with all zeros in it. So it turns out we could, as great exercise, go through and confirm all the properties. But when we get down to this theorem halfway through the page, we see that if we let S be a non-empty subset of a vector space V, then we have a characterization of S as a subspace. S is a subspace of V if and only if, so remember this is an equivalence statement now, if and only if S is closed under the operations of addition and scalar multiplication in V. So it turns out that that's all we need to check for a subspace, not for a vector space, but to show that something is a subspace of a vector space, that's already something that's already known to be a vector space, then all we need to show is that S is closed under the operations of addition and it's closed under scalar multiplication in V. So by doing this up top, we actually have completed all objectives, as long as we've already shown or know that the set of n by n matrices with real entries is a vector space. We haven't shown that technically as a class, but we could get that result from somewhere or go through it and do it on our own anyway. So this is a very useful theorem. That's a nice comment there, just to remind us that this is nice. It cuts out a lot of steps to show that a subspace is, or that a subset is actually a subspace of a vector space. And we're going to see some important subspaces before we're done here. Now, one of these directions makes perfect sense, right? If S is a subspace of V, well, remember the definition is that S is a vector space on its own and all of its elements are contained in V. Well, if it's a vector space on its own, well, then it's closed under the operations of addition and scalar multiplication. It uses the same operations as the host space V. So yeah, that's perfectly, we see that that falls out nice and easy. Now going the other direction is really, it's going to come from the fact that, well, you use both of these properties to go through and show that all the other 8 properties for the list of vector spaces is met by a subspace thanks to additivity, right? Or the closure of addition in this subspace. So in other words, remember that closure of addition in the subspace means that U plus V for U and V, not in the main space, the overall vector space, but in S itself. If we sum any vectors inside the subspace, it stays inside the subspace. It doesn't leave. So that's a really, that's one of the more useful properties. I think you use that for most of this proof. But that's a pretty thorough and lengthy thing. And again, it's not altogether informative to do all the details of that in a video. So we'll move on and look at some more explicit examples. So first example says, determine whether each of the following sets is a subspace of the vector space R4, four-dimensional real space. So by the previous theorem, we only need to check for closure of vector addition and scalar multiplication, and we'll be all set. We're going to accept that R4, I think we've already argued that Rn, at least very loosely, Rn under vector addition and scalar multiplication of the reals is a vector space. Now let's have a look at this. So here's our space. It's the set of vectors of this form: x1, 0, x3, 2, where x1 and x3 are any real numbers. So it looks like 0 and 2 in the second and fourth positions respectively always have to be those values. Well, we take 2 vectors x and y in this subspace. They have a representation that looks like this. They have to be of this form. So that's how I've written them down. Notice when we add these 2 vectors together, everything looks good. x1, y1, that's going to be some real number. So that satisfies that condition of the set. x3 plus y3, that's some real number. That also satisfies that condition of the set. 0 plus 0 is 0. So this matches this form, but something breaks at the bottom, right? When we add 2 and 2, we get a 4 here. Our vectors have to be in the form with, where there's a 2 in the 4th place in the last entry, right? This is not a 2. So this vector is not an element of this subspace. So So of this subset, I should say, we don't know it's a subspace yet. Now we know it's not a subspace because it's not closed under addition. Look, we just took two elements in S in the subset that we're interested in, and we found out when we add them together, we get an element that's not in that subset. So the subset's not closed under addition, so it's not a subspace, right? It's not a subspace of this vector space. That's our conclusion there. Also notice scalar multiplication would break it too. We could multiply this vector by, I don't know, maybe multiply x1 or the vector x by 3. If you do that, you get 3x1, still a real number, so no problem. You get 0 here, so that's good. You get 3 times x3, still a real number. Doesn't matter what real number it is, as long as it's some real number. But you get a 6 here. That's not a 2. We're not in the correct form to be in this subset anymore. So it's also broken by, so scalar multiplication is not closed either. So those are two reasons it's not a vector, subspace. Now, if we fix that, of course we do by replacing that 2 with an x4, then we add two vectors x and y in S together, and we see, okay, real number, 0 where we need a 0. We have two more real numbers at the end. They're any real numbers, so it doesn't matter. So we are, in fact, closed under addition here. We just took two arbitrary vectors, x and y, with no assumptions about them other than the fact that they have this form, since they're in this set, and saw that when we sum them together, we get another object that is in this set. Now, scalar multiplication, we'll check that. We multiply c by this arbitrary vector x. This is also an arbitrary scalar c. When we do so, we get cx1. These are cx3 and cx4 for these entries. Those are all real numbers, so that satisfies our condition. And the second entry has to be a 0 to be in this, to be a vector in this set. That's true in our case of scalar product. And we have that is closed under scalar products as well. So it turns out this is a subspace of the vector space R4. And when you look at them, they're not very different, but there's a key difference, right? One of them remains closed under vector addition and scalar multiplication, whereas the other one violates both. It's not closed under either. So if we have a B is a vector space with 0 vector 0, denoted by this 0 here, then S equals the set containing 0 is a subspace of V. Well, in order to prove this, it's pretty straightforward. We use the previous theorem. We need to only show that we're closed under vector addition. Well, add the 0 vector to 0, to the 0 vector, and we get the 0 vector, right? One of these can use its property as the 0 vector to let the other one be equal to this result. And well, we arrive at a 0 vector, and we know that that is in the set S. Scalar times the 0 vector we saw in a previous result is the 0 vector. So we're also closed under scalar multiplication. We've checked both of those conditions, or shown both of those conditions. So now we conclude that, yeah, the set containing 0 is a subspace of, containing the 0 vector is a subspace of its host space V. So determine whether or not the set of all polynomials of the form here, P of x equals ax squared plus b for real numbers a and b, is a subspace of P2, the set of all polynomials of degree 2 or less, right? I guess I say of degree 2, so maybe we have to go with, they have to strictly have degree 2. That's fine. It won't affect this proof anyway. So we take two polynomials, P of x and Q of x. We have to show that, and we let them be in this set so they have this form, right? We'll write down what that form is for each of them using arbitrary or their own instantiated constants, A1, B1, A2, B2 for P and Q respectively. So put that down, and now we can check our addition. If we add P and Q together, are we going to get a polynomial that's of this form and remain in this set? In other words, have closure under addition. When we do so, we're going to add like terms. The A's are going to add together. The B's are going to add together, because that's what you do with polynomials, right? A1 plus A2 times x squared plus B1 plus B2. So we have something of the form real number times x squared plus constant real number. That's exactly the form up here. It might be a little bit trickier to see. Maybe you do a substitution to clarify, but we have the exact form we expect, and yes, we're closed under addition. We remain in this set because we're still in this form. Now, let's see, for C, we let C be a scalar. We multiply C times one of these polynomials. We're going to get C times A1, x squared, C times B1. Again, we have a real number times x squared. So here's a new A times x squared plus some B, some real number. We're in the correct form, or this form matches this, maybe by substitution if we desired. So we are in the set S. Something that would break it. Maybe we use the field of, I don't know, constant multiples of x, right? So in other words, 2x and 4x, things like that. If that was our scalar field, which we'd have to show that it's a field, but maybe we'll just skip that for now. But so x being a variable, then if we multiply x by this polynomial, we would no longer have the form. We'd have an x squared and then a bx, and that would not match this form. So that's what I mean by the form when I say that. So that would break it, but that's not what we had, so we're okay in this case. Now, subspaces span by a set. This is connecting back. We've already talked about spans of sets, so this is going to be our more important connection to everything. So recall that we have a linear combination of vectors, and if we're talking about the span of a set or linear combinations of vectors in a space V, this is that linear combination for scalars C1 through CK. Okay, and remember that a span of these vectors V1 through VK is the set of all linear combinations of these vectors. So changing these constants as parameters, however we like, makes up the entire span of these vectors. So we have a definition here. If every vector in a vector space V can be written as a linear combination of V1 through VK, we say that V is spanned or generated by V1 through VK. So in other words, if we can make up the entire space with a given set of vectors, then we can span that set with these vectors. We call this set a spanning set for V. Okay, and we'll say things like this set spans V. I think I've already said that one already. Now, on the first example, show that 0, 1, and 1, 0, these you'll recall are E1 and E2, the two standard basis vectors of R2. Show that these vectors span R2. So the way to do that is we let V be any vector in R2. Well, if that's the case, V has a representation of this form. It's equal to some tuple V1 and V2 as entries. So then V is this, and we can decompose that. I can factor a V1, or I can split the sum up as V1, 0 plus 0 V2, and then I can factor V1 and V2 out of that, and I've got my two standard basis vectors right there. Well, that factorization alone, just to decompose this general vector, leads me exactly to where I want to be anyway. If we look closely, V1 and V2 are just some real numbers, right? So this is a real number times 1, 0, a real number times 0, 1, and we see that, yeah, so if I take any arbitrary vector V, it turns out I can generate that vector as a linear combination of my two standard basis vectors. This is actually E2 here, and this one's E1. I might have said that backwards previously, but nonetheless, we see the point. So this is that simple when we have our standard basis vectors. The decomposition is just a matter of factoring out by position in the vector, and then we can generate whichever vector we like in R2 or whatever space we might be in if we have all of our standard basis vectors. That's why they're called standard basis vectors. It's the canonical way to generate the space. Now, second example, show that the vectors 2, 0, 0, 0, negative 1, 0, and 0, 0, 5 span R3. These are not the standard basis vectors, so you might not necessarily expect them to span all of R3. The key thing we're going to see is that they have zeros in different places. They have a non-zero term all in different places. That's going to be what makes this one a little bit more straightforward. They don't need to have non-zero entries in all different spaces in order to span the whole space, but we'll see more about that to come in chapter 4. So for now, let V be a 3 vector in R3. So we decompose it like we did before, only now I'm going to be a little bit more clever about it. I might, first take a step to write V1, 0, 0, and then 0, V2, 0, and then 0, 0, V3. But I've jumped to the next step after that in this line. instead, so I could do that. I could have v1 times 1, 0, 0. Since I wanted 2, 0, 0, I'll just factor a 2 out of there. So I'll divide by, so if we just look at what's happening here, we can multiply the scalar 1/2, the scalar multiple outside that's underneath or against v1 back into the vector, and we get 1, 0, 0, and that's going to be v1, and the first component is going to be v1 when we add it all back together. So we continue this game down the line. V2, I take a negative out of, and that makes the middle negative. V3, I divide a 5 out of it, and that leaves me a 5 in here. So I'm able to recreate my vectors in this list as this decomposition of my general vector. So if we had any vector v, we could form it, or we could generate it from these 3 vectors by using these 3 scalar multiples of each vector, or in other words, this linear combination of those vectors would generate v1, v2, v3. So that one's a little bit less obvious, but we'll see it can be even less obvious as we move through chapter 4, and we'll get a lot of nice results for dealing with that. So next example is to show that the set x squared, x plus x squared, and 1 plus x squared is a spanning set for the space P2, the space of all polynomials with degree less than or equal to 2. Now we're getting less trivial, right? How are we going to generate, how do we know we can generate any any polynomial in this space if we have these 3? So, well, let P of x be any polynomial in P2. So it's going to have this form for scalars a, b, and c, or real numbers a, b, and c. So we need to decompose this and show, so we're looking for scalars k1 through k3. They're based on a, b, and c in the end. In order to, basically, we're looking for a formula that'll allow us to combine these 3 vectors or polynomials in order to make this polynomial out of that linear combination. So what we're asking is, if we do, we're trying to make a plus bx plus cx squared be equal to k1x squared plus k2, this term, plus k3 times the 3rd polynomial in the set. We want to see if we can find k value, k1, k2, and k3 based on a, b, and c such that this will work. If we get something inconsistent, so in this system that we come up with, then we know it won't work. But so what we do is we group like components, right? K1 plus K2 plus K3, these are all the x squared coefficients, is equal to the cx squared, or c in this, so we get this first vector. Now our x coefficients, K2 and K3, so K2 plus K3 equals b, the x coefficient. And then lastly, K3 is a, so we're here. And now we can, this is an easy system, we back substitute, we end up with K3 being A, K2 is B minus A, and then back substituting those values, we get C minus B for K1. We found explicitly values for K1 through K3 in order to rewrite this general, this arbitrary polynomial we wrote down. We can form it from a linear combination of the 3 polynomials in our set. So it's any old polynomial in P2, and it turns out we can find a linear combination, this one here, in order to generate it or create it. And so that means that we could do that for any polynomial in P2. So this polynomial is in this span. It was an arbitrary polynomial, and that means that this set, that the span of these 3 polynomials makes up all of P2. It contains P2. We didn't show this way. We didn't show that it's necessarily a subset of P2, but what we've shown is that if we take an element in P2, we can generate it in this span. It is in this span, so we know that much. In future sections, we might see how to show that they're actually equal to each other. So, or we probably could argue that out in this case too, but more interestingly, we've done the important part with this problem. So that's the more non-trivial version of this. So the last thing we talk about is this linear span of vectors, or for short, we'll say the span of vectors. vectors, okay? I'm just kind of continuing with some of the language here. So remember that the span of these vectors can be written as this. I've been using this already, more or less accidentally in the notes, but this is me formalizing that definition. I think it was obvious to us, but we talk about this set, the span of these vectors, as just being shorthand for this long set notation given above here. So, but it turns out, you know, with this notion of a span of these vectors, that a span of vectors v1 through vk, all of whom are in V, forms a subspace of V. So, well, we could show, you know, if we took two vectors u and v that are in the span of this set, well, then u has some linear combination representation of v1 through vk, and same for w. And when we add these two things together, well, for these scalars c and b, well, we see that, well, we just group the like terms when we add u and v together, right? When we group the like terms, well, those are the coefficients of v1, v2, and v3, and all the way up to vk here. And we see that, well, those are just real numbers times each of these vectors v1 through vk, and that's exactly, or scalars in the field, I should say. So for any scalars in the field, well, these are scalars in the field, so it makes this an element of the span. So that's a pretty easy result to get at. We've only showed closure of addition. Scalar products are somewhat similar, and I'll leave that as an exercise or to be looked up in the book. Now, lastly, determine the subspace of P2 spanned by P1 of x equals 1 plus 3x and P2 of x equals x plus x squared. Well, the span of these two polynomials in this set is equal to any linear combination of these two polynomials. So any a1 real number times 1 plus 3x and a2 or plus a2 times x plus x squared. And well, to characterize these polynomials a little better, this is not wrong, but we can get a better form for the polynomials here. It would look like this. We group the like terms, the x coefficients, the x squared coefficients, and the constant coefficients. We have something that looks just like this. So the subspace of P2 spanned by these vectors is given by polynomials of this form. So they all have to obey this form. And that won't be every polynomial. And that's primarily because this rule right here is a little bit funny, right? If it was just a1 plus a2x squared, that'd be a little bit more simple space, and a1 and a2 could be any real numbers independently of each other. But this middle coefficient, with this somewhat independent term x, is based on the other two terms' coefficients. So that's going to restrict us to a certain class or a certain set of polynomials. So that's it for vector spaces and subspaces. It's a pretty long section with a lot of tedious stuff to kind of learn to do, but nonetheless, I think we ended some nice succinct considerations of vector subspaces. So be sure to do some long form problems, trying to write out all these fundamental details for these things, but also know that we're going to use these in pretty higher level ways and don't always have to labor over the details in this section.